All right, I think it's time. Welcome back, everybody. We do have our usual homework due tomorrow, and I printed it out for you. If anybody needs a printed one, I got a few extras here. Or you can get it electronically in the usual way if you prefer it that way. Let's talk, we are still talking about the convex hull. That's what we were talking about last time. And really the purpose of this is for measuring weirdness of shapes. And why anybody cares about that is so that you can measure these gerrymandered districts. You know, if somebody is trying to draw super crazy shapes on a map, the basic idea is if your shape is kind of like that, this is, I would say, not weird. Whereas if your shape is some kind of crazy wormy thing, this is very weird. But in real life, if you want to actually do serious business involving shapes like this, you need to have some specific way of measuring how weird it is, not just sort of vibes based by just looking at it and say that looks pretty weird to me. You need to actually have a real method for measuring it. And so that's what this thing that we started talking about last time is meant to do. It's called the convex hull ratio. And it's based on starting with a perhaps weird shape and instead also considering its convex hull. So for example, we did a bunch of examples last time, but just to refresh our memory, maybe I will draw a capital letter E here. So what's the convex hull of that? I will say in words what it is. The convex hull is kind of, it's a larger shape typically. It's never smaller, although it might be just the same shape again. The convex hull is the shape that you get by filling in all of the inward sort of intrusions into the shape. Another way to say that is it's the shape you get if you were to wrap a rubber band around that shape. So the convex hull is the, I'll say it in that way, the shape we get if we wrap a rubber band around So in this example, my E, it looks like the thing on the top is a little bit shorter, like the whatever this is called on the top is a little bit shorter than the one on the bottom. But if I were to wrap a rubber band around this shape, it would sort of stretch straight across right there, and then this entire area would be the convex hull. All right. Last time we had a sort of silly handout where you did a whole bunch of convex hulls of various shapes. Or if I have something like this, say, I have basically two big inward curving parts of the shape, and the convex hull would fill in both of those. So it would fill in this side and also this side. And as a little technicality, there's also a little inward curve up there, just because of the way I drew it, which really should be filled in for the convex hull, some like that. And remember, these shapes that you're adding, or these lines that you're adding, should always be straight lines. You shouldn't make them curvy, because if you think about how a rubber band would go around the shape, it would not make them curvy. It would be straight across those gaps. All right. So this is the convex hull. I hope everybody is feeling good about the convex hull. All right. What's the point of this, or what does this have to do with measuring how weird a shape is? This is what I said at the very end last time, and then we'll do some real business with this. So for a fairly nice shape, the convex hull, I'm going to write as CH. The convex hull is very similar to the original shape. The OG shape. All right. What I mean by that is, if I have, say, something like that, which to me looks pretty ordinary for a nice shape, the convex hull would fill in this little bit right here. But really, that's not terribly different from what I started with, right? It's I suppose, slightly bigger, a little bit bigger. This new area here. So I will say for a nice shape, we only add a little bit of area. Right? But for a wiggly, wormy shape, we end up adding a lot of area. So something like, whoa, what happened? I'm going to draw a squirmity-wormity. All right, in this case, to fill in the sort of inward bends, you actually have to go across here with your straight line. And this is a lot of extra area. So for a weird shape, we add a lot of area. And this is how you can tell the difference using the convex hull between a nice shape versus a weird shape. A nice shape is one where the area doesn't change very much when you add in the convex hull, and a weird shape is one in which the area changes by a lot. All right? Specifically, how do we measure this? We can actually boil this all down to real numbers. So this is called the convex hull ratio, which I already said a couple times. I'm going to write CHR, convex hull ratio. What is the definition? This is I'm telling you, this is the definition. The convex hull ratio, it's a number, and it is the area of the original shape divided by the area of the convex hull. All right, that fraction is called the convex hull ratio. The area of the original shape divided by the area of the convex hull. Remember, the area of the convex hull is always a little bit bigger. To get the convex hull, you add in a little bit more area. So when we do this fraction, the number up top, the numerator, is always less than the denominator. That's because the convex hull is just a bigger shape than the original shape. So this fraction, the numerator is always less than denominator. So if you were to actually write out this fraction, it means that the convex hull ratio is between 0 and 1. That's because it's a fraction where the number on the bottom is bigger than the number on top. It means this is some fraction like 3/4 or 5/8 or whatever. All right, and that means as a number, this number is between 0 and 1. Like if you actually do the division on your calculator or something, you get a decimal, and it will be between 0 and 1. Sometimes this is written as a percentage, but anyway, when the shape is nice, because of what I said before, like what that means, if the shape is a really nice shape, then actually these two areas are almost the same. Like that's what we said. For a nice shape, we only add a little bit of area. That means the convex hull area is basically the same as the area that we started with, just adding in a little bit more. So when the shape is nice, it means the numerator and the denominator are almost the same. Can anybody say, like, as a number, what does that mean if you have a fraction where the numerator and the denominator are basically the same? What is that equal? Yeah? A whole number? Yes. Although I wanted to say even more specifically than that. Yeah? It's like 1, right? If you have a numerator and the denominator are almost the same, then when you do the division for the fraction, you'll get something close to 1 or exactly 1 if the numerator equals the denominator. So when the shape is nice, those two areas will be pretty much the same. And so when the shape is nice, the convex hull ratio is close to 1. And this is how you know if you're talking about a nice shape. You can measure this fraction, and then if you get a number that's close to 1, that's sort of like good. It means that your shape is actually a nice shape. Versus a crazy, wormy shape. So when the shape is weird, that is, the area of the convex hull is much bigger than the area of the original shape. That means you're talking about a fraction where the denominator is much bigger. And so when the shape is weird, the convex hull ratio is close to 0. All right, this would be a fraction in which the denominator is much bigger than the numerator. And so this is a single number that you can use to measure how weird the shape is. You measure those areas, and if your answer is close to 1, it means you have a pretty nice shape. And if your answer is close to 0, it means your shape is crazy. All right? Again, you might wonder what's the point of this, because I can already tell by looking at the shape if it's nice or crazy. The point is to have a specific measurement so that you're not just basing your whole judgment on some kind of vibes about how the shape looks to you. This is not about our personal opinion about the shape. We have to be able to measure it and get a specific number for the answer. All right, so there's a big problem if I just show you a shape and ask you to do this. For example, find the original area and divide by the area of the convex hull. If this was like on a test or something, and I drew this picture on the piece of paper and said, find the convex hull ratio, you would have to find the area of the original shape and then divide by the area of the convex hull. There is a major problem, and that is just like, this is a weird shape, and I don't know what the area of that shape is. I mean, in high school, you learned about sort of find the area of a rectangle or a triangle. Those are fairly easy things to work with. But this is like the area of just like a random shape. And how do you find the area of that? That is something that is worth discussing. It's not hard to do, but we need a method to find the area of any weird shape, like not just a rectangle or a triangle or something, right? Shape. We need a method to find the area of any weird shape. I don't know if you've ever thought about this. Trying to find the area of a weird shape is not an obvious thing how you could do that. If you know the formula, like if it's a normal geometric shape, then there are formulas for that. But just like ordinary things in real life, how do you find their areas? It's not really clear how to do that. I would say, I'm going to say this parenthetically because this is not how we're going to do that, but basically this is what calculus is for. So one of the things that you can do with calculus is calculus actually provides a general method by which you can measure the area of any shape. And so if I were trying to be totally like technical about everything, we would do this using calculus, although I'm not into that as far as this class is concerned. We're going to use a more primitive method. This is something that used to be very actually popular for people to use in real life, something called a dot planimeter. This is it will strike you when I explain to you how this works. You may think this is a stupid idea. It's very, very simple, but it turns out to work very well in real life and actually for a long time. Like before nowadays people can use computers to do a lot of this, but before computers came along, people actually found areas using the dots. So I have a delightful little handout here just because there's a lot of pictures that I don't want to have to draw by hands. Sorry, my papers are sticking together. Are there extras? Okay, good. 'Cause I'm running out. I only have 2 here. Is it perfect? Or you don't get one?
I can get mine this one because I have an iPad.
Oh, you haven't got an extra?
Yeah.
Anybody need one? Oh, you got extras. All right. We didn't really run out. You deserve it. Our guest of honor. All right. So this is the dot planimeter. Like I said, this kind of is a stupid idea, or it's at least a very simple idea. All right, I have this here. Can we read this together? We don't have to read it out loud. Finding the area of a weird shape is hard. So the strategy is we superimpose a grid of dots on the picture. So if I want to find the area of this heart shape here, the idea is you put dots in a grid that are separated by a certain distance. So the one that I printed out, these are meant to be 1 centimeter apart, all right? And now if you think about those dots, you can imagine that those dots each are sitting at the center of a square. If those dots are 1 centimeter apart, then these squares have area 1 square centimeter. And if you just count up the squares, that is something that's fairly close to the area of the heart shape, all right? It's not exactly the same as the area of the heart shape, but it's pretty close. It's not exactly the same because you can see like some of the boxes are stretching out and you're measuring too much area. Also, some of the area is not being measured inside any of the boxes, but there's some amount of like over counting, but also some under counting, and hopefully these things will even out if you count them all up. So anyway, how do you find the area of the heart shape? You lay down these dots on it, and when people did this in real life, you could get like a transparent sheet of plastic with the dots printed on it. And then you can just put these dots on top of any shape that you want. Count up the dots that are on the inside. Here, counting the dots, if you count up these dots in here, there are 17 of them, and that means the heart shape has area of about 17 square centimeters. Huh? Any thoughts about that? This is a very simple idea. It's the kind of thing that like any one of us could have come up with this basic idea for finding the area of any shape that you can imagine. All right? It's not the exact area. It's pretty close though. If you want it to be more precise, you could make the dots even closer together. It would be a pain. You'd have to count up more dots. But anyway, this is the basic idea of the dots. Now, there is a question about if you're trying to really do this, like if I were counting the dots, I find it easiest if I'm like have a pencil or something and sort of mark them off just to make sure I get them all. 1, 2, 3, 4, 5, 6, 7. All right, what about, should I count that one or not? It's on the line. There will typically be dots which are on the line. I believe in this, when I said there were 17, I counted the ones on the line also. 1, 2, 3, 4, 5. Is that 17? I lost count, but those are the same ones that I counted in the boxes over here. All right, what if it's on the line? If you look down on your little sheet here, if you think about what should we do if a dot is on the line, if a dot is on the line, that kind of like this one down here, the fact that it's on the line, it means that this little box of area is sort of half in and half out. So really, if you see a dot on the line, the appropriate thing to do would be to count it as a half rather than counting it as a 1. But counting halves is kind of annoying when you're counting up the dots. So this is a slightly fancier arrangement of dots. You will see half of the dots sort of look one way and the other half look the other way. So when you are counting here, we only care about this, the difference between the two dots is only about whether it's on the line or not. And this type of one, if it's on the line, I'm going to count it. This type of one, if it's on the line, I don't count it. That's what all of these words say. And if it's not on the line, you always count it. So when I count the dots here, I'm going to go, this is 1, 2, 3. I am not going to count that one here because it's on the line and it has that other shape. I am also going to count this one over here, which is on the line, but it has the appropriate shape to count on the line. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm going to say that one was not on the line. All right. There is, so here I got 18 dots. So the area is, approximately at least 18 square centimeters. All right. There's always some amount of judgment call about whether something counts as being on the line or inside or outside. Like for instance, right here, I decided not to count that one. Now, because to me, I say that looks like it's outside. Although, in your opinion, you might feel like that ought to be on the line, and therefore you should count it. That's fine with me. So, like when you are doing areas with this method, I would expect my answer and your answer might be slightly different because you're making judgments about something is on the line or not in a slightly different way than I am, and that's totally fine. I don't care about if your answer is slightly different. All right. So anyway, this is how we can find the area of any shape that you like. You put the dots on it and then you just count up the dots. This is annoying to do, but it's very simple and there's no like big idea to it. You just count the dots. All right. Any questions about that? I'm going to do some examples then of finding the convex hull ratio. And I thought, I got another handout here. I thought we should do some real, start in the back this time. What you have here are the 5 different districts in the state of Connecticut for our U.S. House of Representatives. Hmm? All right, so I'm going to, oops. I have this one already. So what you see here are the 5 different districts, and then just for fun, I also put the entire state of Connecticut right here. We live in District 4. I think Fairfield and Bridgeport are like around here somewhere in District 4. But anyway, I put the dots on it so that we could find the areas. So what I want to do here is let's find, like your job is going to be find the convex hull ratio of each district. And this will allow us to say, like using specific measurements, which ones are weirder shapes versus which ones are more ordinary shapes. Like just by eyeball, I would say District 1 looks kind of crazy to me, but District 2 looks pretty ordinary, right? But we want, remember, the whole point of all of this is to have real specific measurements. So maybe I will, let's do 1 and 2 all together, and then I'll have you guys try the other 4 of them. This is a little tedious because it involves counting the dots, but let's do number 1 here. So for number 1, District 1, remember the convex hull ratio is the original area divided by the convex hull area, right? That's the definition of what we're talking about. I'm going to try to squeeze it in the side here. The original area divided by the convex hull area. So first I'm going to count up the original area. That is, I'm going to count all the dots which are inside of District 1. Remember, when they're on the line, you count it if it looks like this. So like I am going to count this one, but I am not going to count this one. All right, that's what the different looking dots mean. It's just, do you count them or not when they're on the line? So let's count. I'm going to mark them off as I go so I don't lose track. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I got 27. Did I miss any? I don't think so. All right, so the original area is 27. I'm making a fraction here, right? The numerator of my fraction is 27. And now we are going to count up how big is the convex hull of this shape. So first, you have to draw in the convex hull by adding, remember, straight lines. This is a thing about, imagine if there was a rubber band around the shape, right? So maybe I'll do this in blue here. You must add in, to get the convex hull, I would have to add in that line. And there's a bunch of little like wiggly things around the side that you also need to sort of close off using straight lines. So I hope everybody remembers how to find the convex hull of the shape. This is what I'm doing. I'm drawing in the convex hull. Something like that probably, and like that. All right. I sort of filled in all of those inward little inny bits. And now we count up the area of the entire shape, including the blue, all the blue area. This area is now bigger. I find it easiest if I already had 27, which I already marked off. So I'm just going to continue counting from 27. Like, you don't have to actually count all of those dots again. There's 27 that I marked in red. And then I'm going to mark additionally, maybe I'll put them in blue, are the new ones that I got. So I had 27. Now I got 28 for that one, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41. And I think that's it. I got 41. And I hope that I counted them all right? So the convex hull area is 41. That's actually, that denominator 41 is the total number of dots in the entire thing. That is the red ones together with the blue ones. All right? I got 27 over 41. And then what is that? Just so that we can compare all the answers. Sorry, there we go. I'm going to use my calculator. Sorry, I didn't do this ahead of time because when I did it before, I counted, I guess I made a slightly different judgment. So I'm going to do 27 divided by 41. I get 0.658 or 66% if you want to round it up. All right? Remember, so is this good or not? Well, close to 1 is really good. Close to 0 is really bad. So this is, I suppose, somehow in between. All right? But we'll be able to use that number to compare to the others. That's the whole point of this. You can compare one number to another number, and you'll be able to measure specifically how weird the shape is. Everybody clear on what we did here? Let's just try number 2, and then I want you guys to try the others. So number 2, to me, it looks like a more ordinary shape. And so I expect the answer here, I got 66% for the other one. I expect this answer to be higher than that because closer to 100%. 100% is like the theoretical best shape. So let's count, first of all, the original area. Those ones across the top, I'm not going to count because they're on the line and they have the bad shape. These ones I will count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, I think. Anybody disagree? Like I said before, if you make a judgment call slightly differently than me, that's totally fine. So here I get 32 as the original area of the original shape. Now we count up the convex hull. So first you have to draw in the convex hull. I'm going to draw with my blue lines. Something like that, maybe. Lots of wiggly business along the bottom here. Something like that. All right, we added a little bit more area with the blue, but not very much more. And now I'm going to count up the dots which are now enclosed by the blue. That would be 1. And I'm going to start at 32 and count up from there. So I crossed off 1. That's 33, 34, 35, 36, 37. 37. All right? That's my denominator. Oh, there's another one. Sorry, 38. Right, I missed this guy right here. Make it 38. 38. All right, and then on my calculator, I'm going to do. You got a question? Yeah.
What about the one on the corner?
Oh, this one here?
Yeah.
Yeah, all right. I was judging that to be outside the line.
Okay.
But if you want to count that, go for it.
It doesn't matter.
Yeah, so I mean, it means that your answer might be slightly different from mine if you make a slightly different judgment. But you'll still be similar to my answer. Yeah. Okay, so I'm going to do on my calculator 32 divided by 38, and this is 0.842, which is 84%. All right, that means this one is nicer than the other one, right? The other one was 66%. All right, see what you think. I would like for you all to try the others, and you can try the entire state of Connecticut too. This one actually to me looks like a very nice, I mean, it's almost a rectangle, right? And so I would expect that the state of Connecticut to be pretty close to 100%. All right, see what you think. these lines that you add in, move these straight lines. So this one should be
Oh, okay.
and this one should come all the way across.
Oh, so it would start here. Okay.
Yeah, all the way. I mean, it's pretty simple, but it should be a straight line. Can I make a suggestion?
Yes, sir. No problem.
This, isn't even just straight line all the way across.
Oh, yeah. Okay.
It's inwards.
Thank you.
Doing good here? Alright. I'll write up here what my counts are. I got 20 over 31 for that, for number 3. I hope your numbers are similar. They don't have to be exactly the same, but. Yeah, they're inside. Right. Yeah, I said 31, so yeah, something you thought was on the line, I thought was outside.
Wait, how do you work this?
Okay. Something similar to me. How's it going? Yes. No, I mean, I don't know if it's gonna actually matter in the answer here, but, yeah, it really should be straight across because your still has this in, right? Well, yeah. I mean, it won't actually change the counts very much, but you know, the shape of this thing really needs to be straight across. Right. Yeah, so like you should count that and that. How's it going? You guys doing okay?
Yes.
Good. Doing all right here? Yes. Yeah, not quite. Yeah. And also the line across the bottom should be straight line. Like your line is still.
Oh, 'cause you're right, 'cause mine's not.
Straight across. Yeah, there.
Is this right, or do I connect?
It should be up there, yeah, because this still has a bend. Doing all right? Can I make it pinky count down here? We still have to. Well, what you want to end up with is sort of what it would look like if you stretch a rubber band around the shirt, and a rubber band wouldn't do that, right?
That's nice.
Straight across. And similarly over here. You guys doing all right?
Yeah. Oh, well, this is my question. So am I counting all of these? Or like, to me they look
I would
like
say
they're
there's,
inside.
yeah, right. If you think they're on the line, then which way?
I think so. Yeah.
I would say that's outside.
Yeah.
I mean, you certainly, like, that's outside. If it's outside, I'm sure. Yeah. All right, I don't think we need to spend all day doing this. I'll tell you what I got for these. So it is important, you know, like I said, your answer might be slightly different from mine. It is important that you are drawing the convex hull properly. So for the full state of Connecticut, I would draw a line over there and then a line going across the bottom, something like that. And I suppose there's a little something right there. And actually there's a little notch up here in Connecticut. There's some weird history about why that is true, but there is an intrusion by Massachusetts, and there's a little something right here. All right, anyway, these are the extra lines that I would draw, and when I counted this one up, I got 44 over 50. So if you got something close to that, then you are on the right track. About number 5, so to draw the convex hull, it needs to stretch across like that, and then also something like this, something going across there, like that, like that, like that. Something like that should be the lines that you're adding in to get the convex hull. And for this one, my numbers were 52 over 70, which is 74% in my calculator. I hope you got something close to that. Doesn't have to be exactly the same, but yeah.
How far off does it have to be, like, because, like, I got 55 over 69 for that one. Like,
55?
yeah.
That means you and I have serious disagreements about what's on the line or not. Like, generally, I'm not going to care if this was like a test question. I would notice if you drew the blue lines wrong and that's why your number is wrong, then I'm going to take out points for that.
Yeah.
But if you just like count, if your count was a few different from mine, I don't care so much.
So like
Yeah.
I got 51 over 74, but my lines are the exact same as yours. Like, is that okay?
Okay. Yeah, I guess. I don't know. Yeah, 74 seems pretty different from 70. Maybe you.
Like, I was counting the ones that were like on the line, I guess.
All of them?
No, but like some.
Yeah, so remember the rule is if it looks like that, you should count it when it's on the line, and if it looks like the other one, you should not.
Even if it's halfway through.
It's like a 50.
Yeah, if it's on the line,
Okay.
yeah, then you don't count that one. Yes?
I got 54 over 67.
That's probably okay. I don't know. I mean, it's hard to. Did you draw these lines properly?
Mm-hmm.
Yeah, then that's probably fine. Any- yeah, sure. Sorry. All right, can we just say the last one here? This is, again, the lines you draw are somewhat important. If you are getting answers that are different from mine because you drew the lines wrong, then that's wrong. If you're getting different answers just because you counted slightly differently, then I don't really care about that. Those are all the extra little lines that I had to put in for number 4. And when I counted these, I got 36 over 39, which is 73%. I suppose I didn't write all the percentages. This 44 over 50, I got 88%. All right. These are all my answers that I got. Sorry, I'm playing with my phone. I have a little clock here. I'm not actually playing with my phone. Okay. So, yeah?
Number 4, for the denominator.
Yeah.
I got 52.
52.
Because I think
Yeah,
there's way
I
more
got
than 3 extra.
Oh, yeah, it's 49, not 39. Thank you. Yeah, certainly much more than 3 extra from the convex hull. Yeah, thanks for that. So, 49. And that's 73%. 36 over 39 is not 73%. That's just a typo I copied wrong from my paper. All right. So, in conclusion, we could say, looking at all of these various figures, as far as these shapes, I would say shapes number 1 and 3 are the weirdest at 66 and 65. Those are, up to my margin of error. Those are basically the same answer. Number 1 and 3 are the weirdest, and I would say number 2 is the least weird, right? And numbers 4 and 5 are somewhere in the middle. All right, I'm just going to write that. So number 2 is the nicest. That's what I said. Numbers 1 and 3 are the weirdest. And then the other 2, 4 and 5, are kind of in between somehow. 5 and 4 are in between. And the shape of the state as a whole is very nice. Although in American politics, the shapes of the states don't really matter, because the states themselves are not drawn in a way to give somebody advantages. These districts, though, individual districts, they often are drawn in a way to give people weird advantages. All right. Here ends what I want to say about the convex hull ratio. This is the first of our two ways. We're going to talk about two different ways. This is the first one by which you can measure how weird a shape is. All right. Great. We got 8 minutes remaining. I think we can start talking about the other one. The other one has a fancier name to it. But the other one is based on a different sort of idea. My old notes here. No, sorry. Here. Okay, so let's talk about the other one. And this has, like I said, a fancier name. So here is another method to measure weirdness of a shape. I would say this method is not better or worse than the convex hull ratio. It's just another way of doing it. Just why do we have two different ways of doing it? Actually, there's even more than two. We're only talking about two. It's because it's a complicated concept, just talking about how weird a shape is. There are a lot of different ways that a shape could be weird or not weird, and there are lots of different ways that you could try to measure this. So here's another method to measure weirdness of a shape, and this is based on area and also perimeter. This is based on not just the area, like the one we just talked about was all about areas. This is about area, but also about perimeter. And this is called, and that's maybe how you can remember this weird word, it's called the isoperimetric quotient. It is also a fraction, like the other one was the ratio of two things. Anyway, you can see this like perimetric. It's about the perimeter. That's why this strange word here has perimeter as part of it. This is another way of measuring the weirdness of a shape. It's based on the perimeter, though. So what's the basic idea behind this? The basic idea here, so I will again draw my usual example of this is a nice shape. And a weird shape looks, something like this. I made it extra weird. All right, this is a weird shape. And I tried to draw these, I don't know if I did a great job, but I tried to draw these two shapes so that they have similar areas. I'm not sure that's really true. The one on the right looks a little bit bigger to me in terms of the area, but maybe I'll just, would you mind? I know you can't do this on your paper, but how you like that? How about that? Now, do they have about the same area? I don't really know, but let's take my word for it. These, I'm trying to draw them so that these two shapes have approximately the same area. So these have, can we just say close to the same area? At least in the ballpark, all right? I'm talking about the area inside, right? And this has nothing to do with convex hulls. It's just about the area inside the shape. All right? These have close to the same areas, but what about the perimeters? I say the perimeter over here is much bigger, all right? Because over here, you're basically just kind of like going around roughly in a circle. I mean, I know it's not a circle, but it's more or less, you just go around the shape. Whereas this one, you're like going back and forth a whole bunch of times. That's a lot of extra perimeter around this shape. So these have close to the same areas, but the weird one has much more perimeter. All right. This is the basic idea behind the isoperimetric quotient. A nice shape versus a weird shape, the way to tell the difference is by looking at the perimeters. The weird shape will generally have a much greater perimeter versus the nice shape. So the isoperimetric quotient from now on, I'm just going to write IQ for isoperimetric quotient, is basically, this is not entirely true. There's some technicalities that I want to talk about, but is basically area divided by perimeter. All right, don't like put that in a box or anything, because that's actually not the real formula. The formula is slightly more complicated, and we'll get to the details of that next time. But it's basically area over the perimeter, so that big perimeter makes the fraction close to 0. All right? And so it's just like the convex hull ratio. When you make the fraction, if it's close to 0, so the IQ being close to 0 is like bad. That means that your shape has way too much perimeter, which means it must be some kind of like wiggly, wormy shape. Versus an isoperimetric quotient close to 1 is good. That means the perimeter is not so much, which means the shape is kind of like a big blob, but it doesn't have lots of wiggles in it. That's the point of the IQ. So the isoperimetric quotient close to 1, or 100%, if you want to write it as a percentage, is good. All right, so in that sense, it works just like the convex hull ratio. Close to 0 means the shape is bad. Close to 1 means the shape is good. All right, so maybe this will be a good place to stop. Next time we'll talk about the technicalities. The formula, the definition is not actually that. It's slightly different. All right, let me know if you got homework questions. I'd be happy to chat about it. See y'all tomorrow.